Today we're going to take a look at some nonlinear systems of equations. So we've been studying linear systems of equations so far. So graphically we've only been looking at lines. And in this section we are going to take a look at some nonlinear systems. So a nonlinear system just means that you have a system with at least one nonlinear equation. But even though one of our equations is going to be nonlinear, our methods of solving are exactly the same as those that we used for solving systems of linear equations. So we know one option is going to be graphing. We can graph the two curves and find the intersection that way. And of course we could do that by hand, or we could use that our technology using a graphing calculator or using Desmos. But if we're wanting to look at algebraic methods, then that means we will be using either substitution or elimination. So substitution and elimination are what we consider our algebraic methods of solving systems of equations. And remember, elimination is sometimes referred to as the addition method as well. Those are interchangeable. So let's look at the following system, and I'm going to demonstrate how we can solve this system using all three of these methods. So let's take a look first at the top equation, which is y minus 1/2 x squared is equal to -3. So this equation, if we were to solve for y and get y by itself, we would add the 1/2 x squared to the other side. So y equals 1/2 x squared minus 3. And this is going to be a parabola. So we're going to review here how to graph a parabola. Hopefully this is something that you remember from earlier in your class. So the 1/2 is going to cause a vertical compression, and the -3 is going to cause a shift down 3. So I'll start by shifting down 3. So my vertex will be at 0, -3. And then off to the side here, let me just remind you how we're going to work with the vertical compression. So on a normal y equals x squared parabola, if we start the vertex, if we were to move to the right 1, we would go up 1 squared, so that would be up 1. And then from the vertex, if we were going to move from the vertex over 2, then we would go up 2 squared. 2 squared would be 4. And if we were to move over 3, we'd go up 3 squared. 3 squared would be 9. But when you have a compression or a stretch, in this case we have a compression because the leading coefficient is a 1/2, then that means we're going to be multiplying these values that we would normally be moving up. We're going to be multiplying these y values by 1/2. So 1 times 1/2, and then 4 times 1/2. So 1 times 1/2, well, that will equal 1/2. 4 times 1/2, that will equal 2. So these are going to be the new values that we'll be moving up as we start at the vertex and then try to create our additional points. So let me demonstrate that. Starting at our vertex, which is 0, -3, I'm going to travel right 1 and up 1/2. And I'll do the same left 1 and up 1/2 from the vertex. Again, from the vertex, I'm going to travel right 2. So I'm going to show you my traveling right 2. But I'm going to go up. Normally it would be up 4 because that would be 2 squared. But half of 4 is 2. So we're going to go up 2 and plot our point there. And same thing, left 2 from the vertex and up 2 and plot my next point there. So let's do that again. This time, let's show if we were to go right 3. 3 squared is 9, and again we're going to multiply that by 1/2. Half of 9 is going to be 4.5. So we are going to be going up 4.5. So from the vertex we'll travel right 3 and then up 4.5. So I'm just going to show that right 1, 2, 3, and then up 1, 2, 3, 4.5, and that's where we'll plot our next point. Same thing, because the parabolas are symmetrical, we will go left 1, 2, 3, up 1, 2, 3, 4.5, and we'll plot that point. I can erase my little hops. So because I have a big enough grid, let's keep going. Let's go one more. So that would be moving from the vertex right 4. So 4 squared is 16, but again we're multiplying that by 1/2. So half of 16 is going to be 8. So from the vertex, we're going to go right 4, and we will go up 8. So that's going to put me at 4, 5, and then from the vertex left 4 and up 8, which will put me at negative 4, 5. And now we have a good number of points on our parabola. We can go ahead and connect the dots, and this is a parabola that has been vertically compressed. So next, let's focus on the second curve, which is x squared plus y squared equals 41. So notice this is going to be the form of a circle because x and y are both squared and they both have the same positive coefficient. So this is a circle that has a center at 0, 0. Just a reminder as to why the center is at 0, 0. That's because we don't have a value with the x being squared. It's like an x plus 0 squared, and same with y. A y plus 0 squared is equal to 41. So that's why the center is at 0, 0. And then you will need to remember that the format of a circle would be x squared plus y squared equals r squared. So my radius squared is equal to 41. Therefore, my radius is going to be the square root of 41. So you would need to get out your calculator to go ahead and estimate that value so we can graph it, and that's approximately 6.4. So you're just going to go ahead from the origin, which is the center of the circle, and go right 6.4, and you're just going to estimate those values up 6.4, left 6.4, and down 6.4, and then just do the best that you can to draw a good circle. So one of the drawbacks of using the graphical method, when we're graphing by hand especially, is that of course there's human error. So we're not going to be drawing perfect circles, and we recognize that our answers are going to just be approximates. So we are looking for the intersection points, and it looks like we have 2 intersection points between the circle and the parabola. And I'm just going to estimate what it looks like on my graph. Your graph might be slightly off from mine, but it appears that my intersections are approximately 4, 5 and negative 4, 5. I might be off a little bit, but we will see now when we move over to the algebraic methods and we use substitution to solve this system next. So moving over to work on solving this system using substitution, I want to solve for one of the variables, and it's going to be easiest to use the top equation and go ahead and solve for y by adding the 1/2 x squared over to the other side. So y equals 1/2 x squared minus 3. And then we will take this expression, 1/2 x squared minus 3, and we will substitute it into the second equation in place of y. So that's going to give us x squared plus the quantity 1/2 x squared minus 3, which will get squared, and that will equal 41. So now you need to very carefully distribute. And if you are prone to making mistakes here, then I highly recommend that you actually write this out twice, 1/2 x squared minus 3 times itself, so that you don't make any silly computational errors here as you distribute. Remember, this is what we call foiling. So when we multiply 1/2 x squared times 1/2 x squared will give us 1/4 x to the 4th power. 1/2 x squared times negative 3 will be a negative 3/2 x squared. And then inside we have the same negative 3/2 x squared. And negative 3 times negative 3 will give us a positive 9. So now we need to combine like terms. I'm also going to reorder this while I'm at it. So I have this 1/4 x to the 4th. I'm going to write that first because it has the largest exponent. And then let's keep track of these fractions carefully. I have negative 3/2 x squared and another negative 3/2 x squared. So that would be negative 6/2 x squared. If I'm adding my fractions, thinking about having a common denominator. But negative 6/2 is really just negative 3. So I really have negative 3x squared when I combine the terms that I have highlighted in green. But then I also am going to go ahead and add that to my positive x squared term out in front. So combining all of these like terms is going to give me a negative 2x squared. And then I'm also going to go ahead and subtract the 41 from both sides because I'm going to need to set this equal to 0. So 9 minus 41 will leave me with a negative 32. So now I have a fourth degree equation. We would call this a quartic equation that I'm left trying to solve. Well, quartic equations will function just like quadratics in that we really want to try to factor it if possible. However, most of us do not care to factor when we have a fraction. So my go-to method here would be to go ahead and multiply both sides of this equation by 4, because if I multiply the 4 times the 1/4, then that's going to eliminate my fraction. But remember, when we multiply the left side of this equation by 4, we have to remember to multiply every single term by 4. Essentially, we're distributing. So this will leave us with x to the 4th minus 8x squared minus 128 is equal to 0. And for a lot of us, this looks somewhat friendlier because we don't have any fractions. And I'm going to go ahead and continue trying to factor this because I recognize that x squared times x squared will give me x to the 4th. And then I'm looking for two numbers that will multiply together to give me negative 128. And those same two numbers need to add together to give me the coefficient of the middle term, which is negative 8. And negative 128 is a fairly large number, so this might be a place where you stop and pause, grab your calculator, and run through all of the different options, the different factors of 128. And it looks like if we used negative 16 times positive 8, that would equal negative 128, and negative 16 plus 8 would equal negative 8. So it appears we can factor this into x squared minus 16 and then x squared plus 8. Now you'll notice one of these factors can be factored further, and that would be the first factor, the x squared minus 16, because it is a difference of perfect squares. So it will factor into x minus 4 times x plus 4. But the x squared plus 8 is not going to factor any further because it is not a difference of perfect squares. So now that we have it fully factored, we'll set each of our factors equal to 0, and that will let us solve for x. So x plus 4 equals 0, x minus 4 equals 0, and x squared plus 8 is equal to 0. So I have x equals negative 4 as one solution, x equals positive 4, and then if you continue to solve x squared plus 8 equals 0 by subtracting 8, and then you will square root both sides and quickly realize that you're not going to end up with real answers here. These are going to be non-real. That means I'm not going to get any additional answers from this factor. So right now it looks like my x values are x equals negative 4 and x equals positive 4. But remember, we don't want to get too excited and think we're done. We're looking for intersections. So we are almost done. We have these two good x values, but we need then the corresponding y values. So now we're going to need to take these x values and substitute them all the way back into one of the originals. It doesn't matter which. Notice in my first step here, I actually had already solved for y. So I'm going to go ahead and use y equals 1/2 x squared and substitute these x values into that equation to find my corresponding y values. So y is equal to 1/2. X is going to be negative 4, the quantity squared, minus 3. Now, negative 4 squared is 16. 1/2 times 16 will be 8. And 8 minus 3 gives us 5. So what this means is when our x value was negative 4, the corresponding y value was 5. But then we have to do the same thing for x equals positive 4. So y equals 1/2, and then we'll substitute in positive 4 for x squared minus 3. 4 squared is 16 again, half of 16, or half times 16 is 8, and 8 minus 3 will give us 5 again. So when x was equal to positive 4, we also got the same y value of positive 5. So these would be our intersection points, and these are going to be the solutions to the original system of equations. Worth noting at this time that our graph wasn't too bad. So when we go back and take a look at our original graph, we were pretty spot on there with our intersection between the parabola and the circle. So now, as I look at that substitution process, it was pretty involved. I want to see if we could possibly solve this system of equations using elimination. So to use elimination, as we have done in the previous sections when we were doing just linear systems, we wanted to get all of the variables on one side of the equation. And you're going to notice back to my original system of equations here that we already have all of the x and y terms on one side. So that's already done for us. The only thing that would be beneficial to fix our setup is we'd like to have the x terms stacked on top of one another. So you might consider rearranging the top equation and writing the negative 1/2 x squared first. So initially, that's what I'm going to do down here for my first step with the elimination method. So I'm going to reorder the first equation, which was the equation for the parabola. I'm going to write the negative 1/2 x squared first, then the positive y is equal to negative 3. And then my circle equation remains the same, x squared plus y squared equals 41. So now I have my variables nicely stacked. Now let's pause here and just kind of take account of all of our variables. You'll notice we have a y term stacked right on top of a y squared term. So there's not going to be a way to eliminate the y variable in this system. However, we have an x squared term on top of an x squared term. So with a little algebra here, we can definitely eliminate the x squared terms. So again, as I mentioned with substitution, you may be a person like me that really doesn't want to deal with the fraction in the top equation. So because I have a negative 1/2 x squared there, I'm going to go ahead and just multiply both sides of this equation by positive 2 so I can eliminate that fraction. And you might ask, why didn't I choose negative 2? Well, remember, when you're doing elimination, you want to have one term be positive and the other term be negative. And so right now, I want to keep that negative sign with the x squared in the top equation. So let's go ahead and multiply. I'm going to write my new equation down here. And again, we're distributing this 2 throughout. So you are multiplying 2 times negative 1/2 x squared, which will be a negative x squared. 2 times y is a positive 2y. And negative 3 times 2 will be a negative 6. And then our second equation will be x squared plus y squared equals 41. And now you'll notice that this is set up perfectly for elimination, because if I add straight down, negative x squared plus x squared will equal 0, and I will have successfully totally eliminated the variable x in both equations in my system. Now when I add my y terms together, these are not like terms, so I'm just going to have to write it as 2y plus y squared. I cannot combine those. And then negative 6 plus 41 is 35. So the reason why I like elimination in this case better than substitution is because now the equation that I have, it's degree 2. It's quadratic. Remember, when we solved this with substitution over here, the equation we ended up here with was a degree 4 equation. And it's always a little bit more complicated when the degree is higher, when the degree is larger. So we're pretty comfortable with quadratics. That's what makes this elimination method pretty nice in this case. So I'm going to go ahead and reorder and write the y squared term first. I'm also going to subtract the 35 so we can set this equal to 0. And then let's go ahead and factor. Remember, if it didn't factor, then we would use the quadratic formula. But in this case, we're looking for two numbers that multiply to negative 35 and add to positive 2. And that would be a positive 7 and a negative 5. 7 times negative 5 will be negative 35, and 7 plus negative 5 is positive 2. So this tells me that y is equal to negative 7 or y is equal to 5. So right now I have two possible solutions for y. But again, we're looking for the intersection, so we have to remember to always substitute those back. This time I'm going to just show you how I could substitute it back into the x squared plus y squared equals 41. just so I show you something different than what we did in the substitution method. So x squared plus y squared is equal to 41. However, we are going to go ahead and substitute the y value that we had. We have a y value of negative 7, and we will solve for x. So x squared plus 49 is equal to 41. But look what happens when you subtract 49 from both sides. We end up with x squared equals negative 8. So we run into the same problem that we had before, that we are taking the square root of a negative value, which means we're getting a non-real answer. And we're only looking for the real values, the intersections. So what that means is that y equals negative 7, it does not yield an intersection. That makes sense because we didn't get a y value of negative 7 in either of the other methods that we tried. So then we've got to finish this off by substituting in a y value of 5 into x squared plus y squared equals 41. So let's substitute our y value of 5, which will give us x squared plus 25 equals 41. Subtracting 25 from both sides will give us x squared equals 16. And then when we square root both sides, we'll end up both with positive and negative 4. Don't forget that plus or minus when you're square rooting both sides. So that means, as we write our answers as ordered pairs, that when the y value was 5, we got an x value of positive 4, but we also got an x value of negative 4. So we still get the same two intersection points, doing it just a slightly different way. So before we stop, it's a good idea to look back and go, oh my goodness, we've done all this great work. What method do you prefer? What's your preference? I'll share with you that my preference, 90% of the time, if I can get my system into a form that lets me use elimination, I feel like elimination is always going to be less work. Substitution is usually a little bit more work, in my opinion. But there's nothing wrong with the substitution method, and in fact, sometimes you have to do substitution if you can't completely eliminate a variable. But if you can completely eliminate a variable, then I'm always going to recommend that you try elimination.